Alright, so tonight what we're going to try and solve are a couple of gravimetric stoichiometry problems. The first one we're going to attempt to solve is going to be number 4. So I've already written out the question and the approach that I'm going to start. So, reading out the question, we're going to see that silver can be recovered from waste silver nitrate solutions by reaction with copper metal. So already what I'm seeing here is a solution and an element, and that's saying to me that this is likely going to be a single replacement, because element plus compound equals element plus compound. That's going to be always a single replacement. So what mass of silver can be recovered by using 50 grams of copper? Alright, so step number 1 is always to develop an equation. So here I'm going to be seeing that silver nitrate solution, so aqueous, plus copper metal can be used to recover pure silver. So I know that I'm going to need pure silver out of this, and whatever is going to be left over my single replacement is going to be CuNO3, and I'm going to put 2 because when I look at my periodic table, that is going to be my common ion. So I'm going to make sure that I include the 2 there, and that is going to be an aqueous solution. Now my equation must always be balanced. I have 1 NO3 on this side, I have 2 on this side, so balancing that. I now have 2 silvers and matching 2 silvers there. This should be a solid. Okay, so I now have a balanced equation to look at. Next up is summary. This is where we just list what we have. This gives us a good idea of where we're starting and where we're finishing. So it's told me that I have 50 grams of copper. Because this is the only value that I'm giving, I'm going to assume that this is going to be my limiting reagent. So I'm going to write that underneath of the appropriate spot so I always remember what I'm working with. So I've got 50 grams of copper. That's my limiting reagent, and that is going to determine my significant digits. So that's my summary. In class, sometimes I talk about 5 steps. You could also think about it like this. So moving on to our third step, we're going to need to figure out how many moles this is equal to. Now, if you are a formula person, you may want to use mass over molar mass. And if you're a unit analysis person, you're going to want to get moles out of this, and you're currently given grams. So you divide this or multiply this by a mole per gram. In both cases, you're going to end up seeing our 50 grams divided by the molar mass of copper, which is equal to 63.55. And again, this is how our formula would look, or you would look at it over here as grams are equal to 1 mole over 63.55, and you would multiply into that with your original 50. So any way you want to look at it, you're going to end up with moles. So for this one, I'm going to be looking at this particular formula, 50 grams divided by 63.55 grams per mole. And that is going to leave me with a trailing number starting with 0.7. I'm going to round off to 2 significant digits here. However, I will state that on my calculator, I am letting the number trail. So I'm not going to be rounding on the calculator forever, but I am just going to show you significant digits across to save space on the page. So our ratio, we will multiply by the unknown over top of our known value. So I'll be taking my trailing number here and multiplying by the unknown, which is my silver, over top of what is currently known, which is my copper. I in class tend to use the term want over what I have, but either works. This is what I have, this is what I want. So I'm going to take that value and multiply it by 2 over 1, leaving me with a new value of 1.57, on and on and on again. And I'm just again going to round that off to 2 significant digits. Now, the last step I've left blank because this one tells me what the actual question is going to want from me. So when I look here, my silver nitrate solution is reacting with a piece of copper metal, and it wants to know what mass of silver. This is huge. This is why reading is so important. So this one, it wants me to come back out to mass. So thinking about this, I need to find a solution or a formula or some sort of unit analysis that turns my moles back into mass. That's what we used here in the beginning. So we're just going to use the inverse. Instead of dividing by our molar mass to get moles, we're going to multiply by our molar mass to turn it back into grams. So I'm going to take this value and multiply it in. And again, in my calculator, I'm leaving it as a trailing number. Multiply it by the molar mass of silver, which is 107.87 grams per mole. And that's going to be moles there. So when I multiply this across, those will cancel out, and it will leave me with 169.7, trailing on and on and on. And I'm just going to show the trailing here because it's going to show me my final rounding. So when I look here, I have two significant digits. So I could leave this as 1.7 times 10 to the 2, or I could convert this into kilograms and call this 0.17 kilograms, or this value in grams. Either is fine. It's just a good idea to make sure that you're always following your significant digits. And I'll reiterate one final time. In my calculator, I am always leaving these as trailing numbers. Let's try a different one. This one is going to be a little tougher. This one is going to include lab skills. So when I look at this one, it tells me a whole preamble about what's going on in a lab. So when aqueous solutions of lead-2 nitrate and sodium iodide are mixed, a precipitate of lead-2 iodide is formed. An excess of sodium iodide is added to the solution containing lead-2 nitrate, and the following data was obtained. So the mass of the filtered paper was 1.04 grams, and the mass of filtered paper and precipitate is 2.89 grams. Find the mass of lead-2 nitrate dissolved. Okay, so there's a lot loaded into this particular question. So first off, it's telling me that lead-2 nitrate and sodium iodide are mixed. Cool. A precipitate is formed. So when I build my equation, I'm going to look for a precipitate. An excess of sodium iodide was added. So that excess tells me that my limiting reagent has nothing to do with the sodium iodide. And then it talks about the precipitate. It gives me some results here. So it gives me a mass of filter paper and a mass of the precipitate. Well, if I take the mass of the filter paper and precipitate and subtract the filter paper, I should be left with just precipitate. So let's start this whole question by figuring out how much material we actually have to work with. So I'm going to start this off before even doing my steps by just figuring out exactly what it is that I'm working with. So one of the ways they'll confuse you is by putting 1.04 on top and then 2.89. So you're naturally going to want to subtract those two values. However, if you do this, you'll end up with a negative number. Instead, flip those and consider that you want to always work with your final and subtract your initial. So to do that, we're going to have 2.89, subtract our 1.04, and that will actually give me 1.85 grams of material to work with in this equation. Now we can actually start solving this. So just like the previous question, I'm going to start with an equation, which in this case is going to look something like this. Lead-2 nitrate solution is going to be reacted with sodium iodide solution. Now, I see two compounds. This is naturally going to lead me to believe that I will be working with a double replacement reaction. So, I will end up with lead iodide lead 2 iodide, I should say, and sodium nitrate. Now, just as before, I need to go through and actually balance this out. 2 nitrates, 1 nitrate. So I'm going to balance that. 2 sodiums, 1 sodium. Balance that. 2 iodines, 2 iodines. Excellent. So we're there. Then I need to write my summary. Now for my summary, I need to pull out a limiting reagent. So I have an excess of sodium iodide, so that's not going to be it. But I do have an excess of 1.85 grams. Sorry, not an excess, but I do have 1.85 grams of the precipitate. Now when I look through here, this was a solution, this was a solution. This is not going to be a solution because NaNO3 has to be one. They are the two members of the most soluble area of our solubility chart. So this is going to be our precipitate, 1.85 grams. Now this can all seem a little bit heavy on the front side just because there's so much interpreting that needs to be done. But if you follow step by step, it's really not that bad. So now we're going to move on to our third step, where we're going to determine how many moles we have. So in this case, again, I'm given a mass, I need moles. I'm going to take that mass and divide it by its molar mass. So grams divided by 461 grams per mole, leaving me with another trailing number. And in this case, I'm going to leave it here. Again, trails onwards, leave it long in your calculator, and then I'm going to multiply that by the mole ratio. Now the mole ratio in this case is going to be what I want over what I have. What I want to figure out is how much lead 2 nitrate was used. What I currently have is how much precipitate was formed from it. So when I look here, I have 1 to 1. So I'm just going to multiply that value by 1 over 1, which will leave me with the same answer. I'm still writing in this step. That way I can see anywhere where I might go wrong along the way. My next step, I'm going to need to figure out what the question is asking for. Again, it's asking for mass, so I fill in that there. And I'm going to, this time, multiply it by the molar mass. 1 moles multiplied by the molar mass of lead 2 nitrate, which is 331.22, and that is going to equal 1.39. I'm just going to put this in here. 1.39, 329, trailing onwards forever number. This is going to add up to 1.33 grams when I consider my significant digits, and when I look in the book, 1.33 grams is found there. This is how you solve gravimetric stoich. However, I am going to say that there really is only stoichiometry and what you're starting and stopping with. It's not so much about gravimetric as it is this is about mass. Next, we'll be talking about gases.